All right, so we're going to discuss a summary of the basics of this property of matter called charge. We're going to build off the ideas we got from the lab where we looked at how tape and foil and paper and even ebonite and glass rod interacted with them and gave us attraction, repulsion, or neither of the two. Towards the end of this, we're going to talk about how to quantify charge. So some mathematics is going to be involved. And it's going to get a little bit confusing at first, but we'll work through it in class. So come in with questions, jot down ideas that confuse you. All right, so when we were doing the lab, we had a piece of paper and a piece of aluminum foil that when we brought our finger up to them, nothing happened. And so we concluded there's no charge. They're electrically neutral. And then when we took the tape and peeled it from the dispenser or peeled it from the table or peeled them off each other, suddenly they became charged. And we knew they were charged because they would affect other things. They would attract or repel them. And so we said, or they're in a charged state. Great, but we never addressed the question, where does charge come from? Does the peeling process or the rubbing process create charge from nothing? The answer to that is no. We don't create or destroy charge, just like we don't really create or destroy mass. So if we don't create charge by rubbing or peeling, then it implies that the charge is already there. So charge comes from really everything. Anything that's matter has charge to it. So we're going to call it atomic matter at the very least. Okay, so your body, your pencil, the desk, the earth, they are teeming with millions and millions and millions in charges, or actually say essentially limitless charges. So that begs the question, why don't we get shocked every time we touch something, right? If there's lots and lots of charge on a bowling ball or a desk, how are we shocked? Because we already know that all objects are electrically neutral. So we seem to have a contradiction. If charge is everywhere, yet everything is neutral, how do we resolve that? Well, we established from our lab that there's two types of charges. And they have opposite effects. And those opposite effects will cause attraction. So what happens is that there are two types of charge, right? Positive and negative. And they're always, or almost always, in equal amounts. So an electrically neutral object has limitless charge, but it has the same amount of each type. And so when you bring a positive next to a negative, they essentially cancel out their effects, and we get overall neutrality. So if you want to charge something, what you're essentially doing is you are separating charges from one body and placing them onto another. So one body has lost some charge, and the other body has gained some charge. The overall charge has not changed, it's just been redistributed amongst the two objects, and that's really important to keep in mind because you can't see this happening, so we have to infer this by using some careful observation and some logic. All right, so let's take a look at the tape. So when the tape was peeled, or if we rub a balloon against your head, why did they become charged, okay, at the atomic level? Basically, what was happened is the negative charges, the electrons, I'm going to put an E here, -1, was basically transferred from one object onto the other. Okay, so a very important point here is when you charge something up, you are stripping the negatives off of one body and you're transferring them onto the other. The object that we add the charge to, or excuse me, in the first blank, we transfer from one object that takes on a positive charge if we're taking electrons off of it. And if we're depositing it onto the other, then that must become negative. Okay, so I mentioned a balloon. So if I have a balloon here that's initially neutral, and I rub it against somebody's hair, and we'll look into more details of this later on, and I rub them together, if the balloon becomes negative, it's because it's taken them from the hair, which leaves it positive. Okay, so the overall charge in the system hasn't changed. It's just a redistribution of that. But keep in mind, only the negatives ever are transferred because they're easily stripped from atoms. The positives are bound in the nuclei, and the nuclei, there's no way you're going to get those positives off them because they're held together by a very, very strong force. Okay, When do objects electrically attract and repel? So we've established already, charged and neutral objects always attract. We saw that yesterday. Like charges always repel. Okay, so positive will repel a positive, negative repel a negative, and opposite charges always attract. And as we pointed out yesterday, you got to be careful when you see attraction. Attraction can mean one of two things. Either you have opposite charges, or you have a positive and neutral, or a negative and neutral. So don't just automatically assume if you see attraction, you have positive and negative. Repulsion always means the same thing. You have like charges. All right, so there's a challenge here. We'll talk about this in class tomorrow of how to determine what the charge of a particular static generator is. So let's go to quantifying charge and finish up. All right, so this is where things are going to get a little bit more confusing. We know that the fundamental carrier of charge resides in an electron or a proton. Right, two of the key components of an atom. We know that an electron has a -1 charge and a proton has a +1 charge. Okay, in fact, that's what the next line is. It's either -1 or +1. But that just meant that there was one extra electron for a situation or one extra proton for a situation. If we had 2 extra protons, we called it +2. If we had 3 extra electrons, we had a -3. But that's not really a quantity. It's just simply keeping track of it. And so when we're dealing with charge transfers, with rubbing a balloon together or to your hair or stripping tape apart, we're dealing with many charges, more than billions and billions. And so we need a quantity, a standard quantity by which to define charge. Right? So this is something you've never heard of before, but I'll try to give you an analogy. So the standard unit of charge, and by the way, the symbol for charge is little q, is something called the coulomb. Named after Charles Coulomb, a French physicist. We'll have more to say about him later on. And the symbol for coulomb is a capital C. Okay? So a coulomb is a quantity that's made up of many charges. A simple analogy is like buying eggs by the dozen. So I might buy 5 dozen eggs. All right? So that's the standard quantity of eggs, even though I know that a dozen is comprised of 12 eggs. So I bought 60 eggs. But the standard measurement is a dozen. So we'll go back and forth between them and give you practice. So notes, 1 coulomb of charge does not equal the charge of 1 electron. Okay? 1 electron is a fraction of a coulomb, just like 1 egg is a fraction of a dozen. 1 coulomb of charge is actually a huge amount of charge. You would not want a coulomb of charge transferred to you. It is roughly the same amount as a lightning strike. Okay? If someone or something is unfortunate enough to be directly hit by lightning from a cloud, roughly a coulomb or so of charge is transferred, and that is lethal. When you got shocked by the generator, you're only transferring about 10 to the -6 coulombs, or 1 microcoulomb. Okay, a millionth of a coulomb is what you feel as a typical spark. So it's annoying, but it's not dangerous. Now the smallest possible charge you can get, this is a very important number, called the elementary charge, and that is in your reference tables symbolized with a little e. Okay, that could be the charge of a proton, it could be a charge of an electron, is given as QE. The charge of an elementary value is equal to 1.6 times 10 to the -19 coulombs. This is a really important number. We'll use it again and again and again. And it's in your reference tables. Let me try to explain that. 1 coulomb of charge, right here, is based on lots and lots of charges put together. Just like 1 dozen of eggs is really 12 eggs. So we could turn that around and say, if I'm looking at my egg analogy, 1 egg is 1/12 of a coulomb, or of a dozen. Okay? If I have 5 eggs, then it's 5/12 of a dozen. So what we're saying here in this statement is that if we only have 1 electron out of the many that make up a coulomb, you're only going to get this fraction of a coulomb, a tiny amount. So we could turn that around and say, well, how many electrons would we need to make a coulomb? Well, we just take the reciprocal of this number. So if we take the reciprocal of 1.6 times 10 to the -19, we find that there are, I'm drawing a blank here. me look that up. It's, hold on, I can do it. 6.25 times 10 to the 18th. How much charges are in 1 coulomb? Okay, so let me repeat that in terms of eggs. We can say that there are 12 eggs in 1 dozen, or we can say there is 1/12 of an egg, excuse me, there's 1/12 of a dozen for every egg. So these two numbers right here, both in the reference tables, are reciprocal values of one another. So we just got to know when to use one or the other for the situation. So let's do a practical problem. Okay, let's scroll down a little better. All right, so a question we asked about how many charges. Charges is Q. Okay, excuse me, I take that back. Charges are elementary charges, electrons, are transferred from the Earth to a static generator. So what do we know about the amount of charge? We said above that the amount of charge, Q, that is transferred is about 1 times 10 to the negative 6 coulombs. Okay, so what I'm asking is, how many electrons does that correspond to? So this is how I suggest you set it up. I'm going to give you a method. We're going to make a little table. Okay, I'm going to take my quantity, 1.6 times 10 to the negative 6th. I'm going to put it up there, and I'm going to put a 1 underneath that. Okay, then I'm going to take my conversion factor. If I look up at my conversion factor, I see that it says that there is 1 charge per this number of coulombs. So I'm going to put 1 charge per 1.6 times 10 to the negative 19 coulombs. In other words, I put this on the bottom because I want the C's to cancel out right here. So what do? I take this number and I divide it by that number. Okay, I'm not sure why I have the 1.6 there. That should just be 1 times 10 to the negative 6. So if I do 1 times 10 to the negative 6, and I divide it by 1.6 times 10 to the negative 19, I get 6.25 times 10 to the 12 electrons. So when we charge up that static generator and touch it, this is how many electrons are being deposited on you, over 1 trillion. That might seem like a lot, but it's actually a really small number compared to things. Another example we could do is, let's say we have a drop of oil, and we say that a drop of oil has a deficit, meaning it's lacking 2,300 electrons. What must be the charge of the drop? So now we're going from E's to charge, Q, in coulombs. Whereas in the last problem, we went from Q to E's. So again, I'm going to set up a table. I've got 2.3 times 10 to the 3 electrons, right, over 1. Always put it over 1. And then I've got 1 electron per coulombs, but I want to put the 1 electron on the bottom because I want those to cancel out. And I'm going to put 1.6 times 10 to the negative 19th coulombs here. So since they're both on top, I'm going to multiply those two numbers. And when I multiply those numbers, should have done this beforehand, I get 3.68 times 10 to the negative 16th coulombs. So a lot of charges gives me still a small amount of coulombs. It's 2,000 times greater than that of 1 electron. Okay, we'll do example 3 in class. So please take a look at these last 2 examples and come in with any questions, because you got to be able to do that. And once you get it, it's not too difficult to do.